All right. Thank you, everyone. So today's lecture is the third in the series of our dark matter lectures. Just as a reminder, the first lecture was on evidence for dark matter and constraints on its properties. In the second lecture, we discussed the growth of structure in dark matter, the matter power spectrum, and I introduced scalar wave dark matter, right? Scalar field dark matter. Today's plan is to continue with scalar field light dark matter, and I'm going to tell you about three phenomenological implications. One, which is gene suppression, and two, which are more in the nonlinear regime, which are about interference and solitons. And if you and I are not too hungry by that time, maybe I'll discuss formation mechanism, otherwise of this type of dark matter, otherwise we'll do it tomorrow. So just like yesterday, I will put forth my goal and we'll see whether we get there or not. So my goal today is to explain to you this cutoff in the power spectrum. That's one, that's the gene suppression. Then I will move on to discussing dynamics of these fields or this type of dark matter in the nonlinear regime. And I want to tell you in that regime two important effects that arise in this type of dark matter. One is interference, and the second one is solitons. Okay, so there are three things: gene suppression, interference, and solitons. Those are our goals for today, to understand that. Okay, so let's begin. And as always, I'm going to go through very quickly with a review of what we have covered in the last lecture, and then move on to new stuff. So very quickly, we were discussing spin zero or scalar dark matter. It could be QCD axions, fuzzy dark matter, ultralight dark matter, give it the name that you want. We said that we were going to describe it by it's well described by a scalar field, classical scalar field. The action, including gravity, is written on the second line. It included a potential which had a mass term, because we need the dark matter particle to be massive, otherwise it can't be non-relativistic. And we had an interaction term both with itself and with potentially the standard model. In this first treatment, I told you that we are going to ignore these self-interactions lambda and this coupling to other standard model fields. So that's where we were. Varying the action with respect to the field chi or the metric, you get Einstein's equations here, and you get the Klein-Gordon equation on here. Last time I went from here to describe to you the non-relativistic solution of these equations. But Meredith correctly pointed out that I didn't do one of the basic things first, so let me do that first. Okay, why is this a good dark matter candidate? So let's do a very simple case of take this equation, but assume that this field is perfectly homogeneous, meaning it's not a function of space. Okay, so it's just a function of time. Then the Klein-Gordon equation becomes this equation right here. It's just second time derivative with a mass term, and this is the Hubble friction term that comes about. If you are in a regime that the Hubble is much smaller than the mass of the particle, then the solution to this equation is given approximately by this function. Okay? So it looks like something that's, if you ignore this, the first part here, then it's a harmonic oscillator, because if I ignore the Hubble term here, it's just a harmonic oscillator, so the cosine is a solution. But because of the Hubble friction, you get an extra time dependence here, which is 1 over a to the 3 half. Okay? And this you can try to solve for yourself if you want. You can do it by WKB if you want to get a better approximation. So this solution now, if I take this solution and try to construct the energy density of this field by taking the T00 component of the Einstein equation, then you will find that the time derivative of the cosine gives you a sine. So this is sine squared, this is cosine squared. They add up to unity, as a result of which you get a energy density that goes like 1 over a cubed. This is the energy density of pressureless stuff. This is what we want. So that's why this is a decent dark matter candidate. for this homogeneous case. You can also do it for the inhomogeneous case where you have fluctuations, you have no homogeneous mode, you will find that the same result holds. As long as it's non-relativistic, you will again get this 1 over a cubed behavior. Okay, so it's a good dark matter candidate. Okay, so that's for the relativistic case, right? So that we didn't have to go to non-relativistic things to, or go through the Schrodinger-Poisson system to get that result. But to solve the system, especially in the nonlinear regime, it's convenient to go to the Schrodinger-Poisson system. And that's what we did last time, which is we started with this equation. I did a field redefinition and derived for you under appropriate approximations, subhorizon and slow time variation for this field psi. I derived the system called the Schrodinger-Poisson system. This is the Schrodinger equation. This is the Poisson equation. The scale factors and stuff appear because we are doing this in an expanding universe. I tried to stress that psi star psi is, you should think of this as the number density of your dark matter particles. So rho, which is m times psi star psi, is the mass density. If you want to see squared there, it becomes the energy density. The other thing I forgot last time, which I'm embarrassed, is I never showed you why this has anything to do with non-relativistic. So why were these approximations relevant for non-relativistic things? What was the relevant thing? To understand this, let's look at a simplified version of this equation, just a free Schrodinger equation, and now plug in this approximation on this side. Right? Time derivative, I said, is much less than m psi. So you plug it into this side of the equation, and immediately you will find that that tells you, if you think of the gradient like in Fourier space like k, it will tell you that this approximation here, this statement right here, is the same as saying that the rest mass is much bigger than the kinetic energy. And that's what non-relativistic means. So that's why this assumption here corresponded to non-relativistic fields. Okay. So we did this, we derived this equation. Then I told you that the good thing to do is to bring these equations in a form that we've already discussed before. So what we did was we did what is called the Madelung transform. We defined psi in terms of it's a complex field, so you can have an amplitude and a phase. So rho is the square root, or rho is the square of the amplitude, and theta is the phase. We defined a velocity, which is a gradient of this phase. And once we did that and plugged these definitions back into the Schrodinger-Poisson system, which was there on the previous page, I just took those definitions and plug it into this equation. Then I get equations that we are now hopefully familiar with: mass conservation, momentum conservation, and the Poisson equation. Same equations that we had done for pressureless dust. The key difference was that there was an extra term that appeared here, and that extra term comes about as a Laplacian of the square root of the density. So these are the new equations that we get, similar to before, but with one difference. And this is coming from the wave dynamics of the system. Yes? Of theta. With this, the first equation here? Yes. I mean, it's a complex field, so I'm just writing it as the amplitude and a phase. So that's the definition of theta. Okay, so these are the equations that I want to now work with. And my goal is to get this equation. I will think about first linear perturbations and get an equation that was similar to what Rogerio had introduced in his third lecture. And we'll compare and contrast what differences come up. Okay, so first, the homogeneous part, you can actually solve the system, set V to 0, and just consider homogeneous part, and you will again get an immediate solution that rho goes as 1 over a cubed. No surprise there. I showed you for the relativistic case. It's just doing it again. Now let's think of perturbations. So I'm going to think of perturbing the density around the homogeneous value by a small amount, delta. This is a fractional density contrast. And I'm going to assume that the velocity and this density contrast are both small compared to 1. Okay? Of course, V is dimensionful, but we are always thinking of V over C. So these are both small compared to unity. And now I plug it in to these equations, and we do a process called linearization. What do I mean by linearization? Anytime I see something quadratic in V or delta, I drop it because they're small. This is a dangerous business. Okay? You should always be careful about doing such things. Here we are going to first do it blindly and see what the results are. And I'll tell you what we can miss out on by doing this blindly. So we start by, I've just taken this perturbed density, plugged it into the equations, and I've now derived the linearized versions of the top part. So there is the first equation right here comes from mass conservation. The second equation comes from momentum conservation. The third equation is just your Poisson equation. As before, the next thing you do is you can combine these three equations. Can somebody see any extra terms compared to what you are used to before? Which equation has an extra term? Sorry? The second one, right? So notice this would just have been gradient of phi, right, which is a gravitational acceleration here. But now we have this extra bit here. Okay? This extra term comes about. It's just this grad q term that is being translated. So again, just reminding you that that term is being carried through. It's not being lost. I combine these three equations. So I manipulate them, I combine them. Everyone should do this exercise. It's kind of fun because you're like, oh yeah, I plug it back in. I do it once, I plug it back in. It's a fun little exercise. You do this and you get this new differential equation just for delta. So I've eliminated V and the gravitational potential from these equations. So the only thing that's left is delta. Notice this equation should look quite similar to the equation that we are used to. It's almost identical except for this extra term, this gradient to the power 4. This is again coming from that Q term that was introduced because of wave dynamics. Yes?
The Q term can be seen like a relation of the logarithm power.
Right. A lot, because yeah. So I did rho bar 1 plus delta, and I kept linear order in delta. Okay. I think in this regime it's okay. I mean, you can do it more carefully. Of course, you can keep extra terms, and people do. People do keep extra terms, and you get corrections. But I think the effect that I want comes about at this level. Yes.
Where does the Q term come from?
It comes from okay. So, sorry. Here's the equation. So this is the equation for the dynamics of this delta. This is the density contrast for dark matter, and we want to understand what the solutions are. This is a partial differential equation. PDEs are hard. Of course, we are going to deal with them in a moment, but it's a linear equation. As we have learned, linear equations are easy because we can go to Fourier space. Go to Fourier space, and the equation looks like this. There's a lot of things on here, so I'll break it down slowly. The Laplacian, when you go to Fourier space, just becomes, or the gradient to the 4 just becomes k to the 4th. So that's why there's a k to the 4th here. I've just rearranged things. I've divided by 4 pi g rho here and then pulled it out just to make it look nicer. So now it looks like k to the 4th. No. What did I something happened. Sorry? Tap it? It needed some convincing. Okay. Right, so this k to the fourth term appears here. It's an extra term. And I have a scale here, kj. Okay, how did I define kj? It's just by moving 4 pi g rho at the bottom, it becomes this term right here. Okay. In the literature, this is called the gene scale as well. It's kj, and if you simplify this, what have I done? G rho, if you're in matter-dominated universe, G rho is just h squared. So that's where h is coming in. I simplify things, and you just get this kj scale in terms of mass, the Hubble scale. What is nice about this, the way to remember this scale, is it's a geometric mean of mass and Hubble, okay, at the time that you're interested in. So that's how this scale comes about. You can also think of this as a scale-dependent sound speed. Okay, so that's another way of thinking about if you remember the equation that Rogerio had introduced with cs squared k squared, the sound speed is scale-dependent as well now. But it's either way you think about it, there is an extra piece here that depends on wave number. So let's think about, this is the extra term. When k, the wave number, is small compared to this characteristic scale, the genes k, then this term is irrelevant, right? So on small k, you can ignore this term and you go back to this equation here. But when k is larger than kj, the nature of the equation itself changes. Why? Because if this term is larger, this minus is no longer relevant. And now this starts looking more like a harmonic oscillator type equation, because a positive frequency squared. So now this will give rise to not growing solutions, which we had when you were using this part, the -1 part, but now you have something that does not grow, it oscillates. So this term is making a crucial difference, that when this term is negligible, you get usual growth, you get back to our previous picture, but when this term is large, you will get a very different behavior. So that is what I am stating here. If k is less than kj, you get the usual growth. This is in matter domination at the moment. We can do this in radiation domination as well. And then otherwise you have oscillatory solution with other time dependence as well in here. So what does this tell us? That this extra term allows structure to grow well when k is small, that is on large length scales. When you go to sufficiently small length scales, or when k is large compared to this scale, you will not allow growth to proceed in the usual way. And that is precisely why there is no growth at large scales in these metals. So if you have this gene scale roughly around here, okay, then beyond that k, there is no growth of structure, or it cannot grow efficiently. So you have a suppression compared to the original case. So that's how you get this. Now, the gene scale, notice it depends on the mass of the particle. So it clearly depends on the mass. So I want to make, if I make the mass very heavy, then the suppression gets pushed to this side, to the right. But if I make the mass light, it gets pushed closer and closer to where we have observations. So this should give you a sense that if you haven't seen the suppression in the data, it should give you a constraint on how light the mass of the dark matter particle should be. So using that, let's say that we take this observational scale from, which is taken in this reference, was taken from Lyman alpha observations, about 10 megaparsec inverse. And if we say that the gene scale is beyond this scale, then that gives you a constraint on the mass of the dark matter particle of 10 to the minus 21 electron volts. So this is our first constraint. By using what we have learned, we are getting a constraint on the mass of the dark matter particle. So this is, I like this because it's connected to a linear perturbation theory that we did that had to be true for all CDM models, and now we are seeing that because we are not seeing deviations, we are putting constraints. It would be even more exciting if I were to say we see deviations and here is the mass, but we are not in that situation. So don't expect that for any of the conclusions today. It will always be constraints. Okay. Yes.
For other bosons, we get a kind of similar constraint.
Sorry, for
other bosons, other spin one.
So it's tricky because you have to decide whether, so this is true if you start out with a homogeneous field background. If you can generate a homogeneous field background, then the constraint will be similar. But at least the scenarios, if you produce other bosons with either during inflation or after inflation from simple scenarios, you don't get other spin bosons, you don't have a homogeneous mode. So you get power on small wavelengths, which in turn leads to a bit of free streaming. And that can be more effective than this cutoff that's here. It actually comes in earlier. So you can get a constraint which is of the order of 10 to the minus 18 electron volts. So it's better than this for that. But again, there are caveats to this. So I'll come back to this towards the end of the talk a little bit when I'll generalize. Okay, so this free streaming effect that I said we miss out on because we linearized blindly, completely. We didn't see it. And it was okay here because at the back of my mind, I'm assuming that the dominant contribution to the energy density is from the homogeneous mode of the field. Okay, so that's why it was okay. But if you include those fluctuations or those are the dominant modes, then you have to take that effect into account. Okay. Now it's time to do, I will put on my other hat. I will move away a little bit from, I will tell you analytic stuff, but there'll be a lot of pictures, lots of movies, because this is the simulation part of things. We are going deep into the nonlinear regime. I will always start with the physics and tell you what is the understanding of it, and after that, I will show you movies with full nonlinear simulations to see how we see those effects. So we are going to, first let me just tell you the simplification I'm going to make for our discussion. So here is a simulation of dark matter using scalar field dark matter, ultralight regime. Here is the usual CDM simulation with just point particles that we do. They look rather similar. Okay, so on these large scales, where we are thinking of linear power spectrum, or even on the scales much larger than 10 megaparsec inverse, you don't see much difference between them. But if you zoom in to one of these regions, okay, in say here or here, you will start seeing lots of differences. In the scalar dark matter case, here is an example of what you would see when you would zoom in. You see these speckle patterns. Okay? These are the interference patterns that we are going to be discussing. And there is a core here. It will turn out that this is a soliton. Okay? So that's also something new that comes about. But all of these effects are on small scales. They are on scales that are where expansion is not so relevant anymore. Okay? So I'm going to make the assumption or approximation that I'm going to ignore expansion because I'm thinking now about small nonlinear scales. Okay? This will make our discussion easier so that I don't have to carry the scale factor and Hubble and so on around. Okay. So small nonlinear scales, that's where we are going to think about. And the first effect that I want to describe and explain to you is what is this, sort of this interference pattern that you see? What is going on? Where is this coming from? Okay. So this, luckily, is the simplest thing to think about. We have wave dark matter. They are waves. And the one thing we know about waves, the first thing we learn is you add two waves and you square them. The sum of the squares is not the square of the sum. Right? There is interference. That's what this is. So let's take two waves with some wave number and some phase, A and B. You add them together and square them. Why am I adding them together and squaring them? Because the modulus squared is what the density is. Right? That's psi star psi. That's what the density is. You have to add them first and then square them. If you do that, you will get terms which are just the amplitude squared, and then you have the interference term. Now, this interference term right here, the fact that this need not be 0 is telling you the square of the sum is not the sum of the squares. How do we translate this into some scale, some pattern that we see? So this difference in momenta, typical difference in momenta, roughly is just a velocity dispersion that you would expect in the system. So that velocity dispersion is mv, where in the usual sense you should think of, sorry, this should be v squared, not v. V squared is gm over r. That sets a scale. Okay, that sets a scale of on what scale you will see this interference patterns. So if you add a bunch of such waves, not just two, but many of them with random phases and momenta and amplitudes drawn from some distribution, you will get some picture like this for the density. You get peaks and valleys, peaks and valleys, peaks and valleys. This is just coming from interference. What is the length scale? How separated are they? It's related to this MV. So it's just, this is just 1 over MV. That's the scale. That's the length scale of the pattern. These patterns are also not stationary, right? There's time dependence, there's waves, they're doing all sorts of things. So there's not just a length scale to these density patterns, there's also a time scale of coherence over which they change. And that time scale is 1 over MV squared. So this is how this interference pattern comes about. And again, you can do this by dimension analysis. H bars are missing here because we have set them equal to 1. Yes.
Any question about
Yes.
simulation?
Yes, please.
So usually in cold dark matter, you have this just n-body particle, right? Any particle, whatever mass. Here, how do you put this ultralight dark matter in this? What is a particle in your simulation?
Good. There's no particle, there's a field. So we solve the Schrodinger-Poisson equation directly. So you solve the full, it's a PDE, you solve it on the lattice, and you just time evolve forward. So in an expanding universe, and you can do it. I mean, now it's very computationally expensive to do this, but as I will show you, the codes are quite well developed now, and we have taken a lot of advantage because, as I will show you, this equation we are solving is actually been solved very well before in condensed matter systems, because this is also an equation that describes bosons and condensates. We just have gravity, so we have to deal with that. So we have learned from that, and we can use those techniques. There's techniques called kick, drift, kick. Again, sorry, if I go into too much numerical jargon, stop me. So there are all these techniques that have been developed to just solve these PDEs efficiently. They're usually pseudo-spectral. So you solve part of the steps in position space and part of them in momentum space. So again, there are many algorithms that do this.
But again, what we plot is
Yeah, because that's the density. That's a physical.
seeing those pictures.
Yes, psi. It's a density. Right? That's what we plot.
How do you compare with CDM? Because you have a plot that you compare with CDM. How do you compare this with CDM?
So density, right? Mass density is mass density. Mass density is mass density. So I can do a comparison, apples to apples comparison. Excellent. Okay. Thanks for the questions. Let's move on. So you now know something about these interference patterns, okay? What they are. Let's put them to use immediately. So let's see, what can we do with these patterns? Can we get a constraint now? We did this derivation for gene scale, we got a constraint. Now let's use these interference patterns to again connect with observation. So here is a simulation of this is not actually a full real-time simulation, I'll tell you how this is done if you're interested. But by Dalal and Kravtsov, what they did was they simulated what these interference patterns, or what the density and interference patterns look like in a halo. This is a halo of an ultra-faint dwarf galaxy. Okay. And these two are just different they're the same. The homogeneous density profile, if you were to average over these patterns, and everything would be the same. But the difference is that the mass of the particle is different in the two. What that means is that the de Broglie scale will be different, so the scale of these interference patterns will be different. Here it is lighter, here it is heavier. The heavier the particle, the smaller the de Broglie scale, or this wave interference scale, so you see finer structure. So that's what they did. Why did they do this? And this again is not, the simulation is not new, the people have been doing this for a while. The interesting thing that they did is now they thought about, okay, in these are dark matter dominated galaxies. Let me look at, and I can look at the velocity dispersion of orbits of stars in these galaxies. We have an expectation of what this dispersion should be based on simple smooth models or CDM models. If we were to find that the dispersion is not significantly different than that, then it turns out it will give us a constraint on these interference patterns. How does this work? Well, these interference patterns are density fluctuations. So a star that is going around, it sees, since there are density fluctuations, there are gravitational potential fluctuations, so it gets kicks, right? It sees, oh, there's a little bit higher density. Oh, there's a little bit lower density, higher density, lower density. So it gets heated up in the sense that its orbit gets mixed a bit. Okay? So that heating up is an effect of these interference patterns. So they said, well, we should, if there are these interference patterns, you should see heating. So they looked for it, and they said, well, there's no significant difference from the usual expectation without interference patterns. And this heating, we can go through the calculation, turns out to be proportional to the variance of the density and this de Broglie wavelength cubed. So it's 1 over m cubed because de Broglie goes as 1 over m. Okay? So putting this together, the fact that this wasn't significantly different than what was expected, they were able to put a very good constraint on the mass of the dark matter particle of 10 to the minus 19 electron volts. So just this idea that, look, we have waves must interfere. There's no model dependence there. Interference patterns should be there that lead to density fluctuations. Let's see if we can constrain it. And here is an example. This idea, by the way, was there before. It had already been proposed to look for a puffing up of stars in our Milky Way disk. Again, because these would produce some jitter. This was Church et al. But there the constraints were weaker. This, by selecting a good system, they were able to get much better constraints. And I think this is, in terms of independence from formation mechanisms and things like that, this is the best constraint that I can think of. If you include some more information, you can get something better. Yes?
Do you get Navarro Fraser White?
You do, yes.
Small scale?
Yes, not at small scales. Not at small scale. So it will change the core. Yeah, so there's a core. So I think the general intuition you should have is whenever you are on length scales larger than the de Broglie scale, everything that you know about CDM should be the same. Okay. So when you get to these scales, you will start seeing differences. In the center, we will talk about a core. Yes, so the small scales. So. Any other? Yes. Yes. Yes.
So this interference pattern is not static, right? Do you have an idea of how fast it's changing in time?
So it's pretty slow. In the sense that it's, let me remember. So what is, I think for 10 to the minus, I have to do the calculation. So I think a year is lambda over v, right? So lambda is, we have given it on what number it is, but I think it's, the Compton scale for 10 to the minus 22 EV was about a year. So you have to divide by 10 to the minus 10 to the, you have to multiply by that, by 10 to the 6. So about 10 to the 6, I think it could be of the order of 10 to the 5, 10 to the 6 years. If I'm taking v equals 10 to the minus 3c. So I think I remember the Compton scale. Does anybody else remember? Is that right for people who work on fuzzy dark matter? 10 to the minus 22 EV. What is the Compton time? Okay, I have to check. I don't remember. Yes. Yes. Constant? Yeah.
Yeah.
Wait for.
Why is the direct?
Good. Give me a few slides. We will get exactly to that. Okay. So we'll talk about the core in a moment. Here, by the way, they don't actually have a true core because this is not a true simulation. If you're actually to form these things, there would be an even more prominent core than you can see here. Yes.
Scales are very small, and inside the core of the galaxy is a black hole. These are very small. I think it's really observable.
Which one?
These dynamical.
Yes, because I mean, ultra faint dwarf galaxies. I don't know if there is a giant black hole at the center. There's nothing. Sorry? Yeah, this is much better to do with these. I mean, Milky Way is complicated. There's too much stuff. There's too much baryons are doing too much things, right? Too many things, so it's complicated. So you want to go to systems that are clean. So you want to go to dark matter dominated systems, which are ultra faint dwarf galaxies. So that's why they were able to get a constraint. Okay. From the Milky Way, you get a constraint at 10 to the minus 22-ish EV, which is similar to what. So it's not much, you can say. But you want to go, the good thing they did was they chose the right system to do this. Okay, great. Yes? Radiative from baryons? These systems have very few, baryons are subdominant. They're very subdominant compared to dark matter in these systems. So that's why these systems are good to do them. Somebody, okay. All right, let me give another example of using interference patterns. We learned what they are, so we should definitely put them to use. Here is an example using gravitational lensing. Again, interference patterns are density fluctuations, light, which creates potential fluctuations, which light sees. Okay. So what these, so Powell et al., and this is again in a series of, this is later in the paper series, this is more recent, they were looking at images of these jets from quasars, okay, and they should, unless there's something really funny going on, they should have some structure, they should be relatively straight, they should look like what we expect them from physics. So they say, well, we don't, however, if you increase the amount of interference, meaning you go from this, look at the mass going from 10 to the minus 21 to 10 to the minus 22, your image gets heavily distorted. So the fact that you don't see this distortion, again tells you, well, the interference patterns can't be too important. If it can't be too important, it gives you, interference patterns are related to the mass of the particle. Again, you get a constraint on the mass. So with this observation from lensing, you get 10 to the minus 21 eV. This is not as great as the previous one, but still independent. So these are good things to be done. And both of these things I will come back to tomorrow when I discuss higher spin dark matter, not just scalars, and see how these things change based on that. Okay, it's a simple change. So we'll talk about that. So a fraction of dark matter. So they also had that as a fraction. How much of this fuzzy dark matter makes up all of the dark matter? So they had that fraction as well. All of dark matter or in this lens, I think. Which ones?
63.
I think this was, I forget, this was through the data, and I don't know. It's a truthful answer. I don't know what they were. I think they were trying a lot. Which ones?
This picture.
What do you mean, simulations? No, these, yes, they're simulation, but they're sort of, I think they've done all of them. It's just for demonstration. They had a full series of things that they did. And they were basically trying to analyze with lots of different parameters what the best thing they could get out of, right? But this is just for demonstration. This is not, their paper is more about statistics. This is just, I took the images from that paper. Yes, please.
Will there be interference when self-interactions, say positive, are present, since the length scale of the system will now be set by self-interactions?
Interference will always be there. It's just waves. Doesn't matter what interactions you put in. The question is at what scale and how different they will be. So as long as, I would say that for not to, whenever there is a characteristic length scale in the problem, meaning say the virial velocity gives you a characteristic length scale, or the self-interaction gives you another characteristic length scale, you will see interference patterns. The scale, again, is correct that it could be modified by this, but if it's dark matter and it's relatively weakly interacting with itself, then the dominant scale will still be the de Broglie one. You'll have slight modifications, but I think this will, we're talking about, I'm always writing a twiddle. So it's order unity numbers. So I think this should be fine. But thanks for the question. I will show a simulation with self-interaction and you'll see the patterns there as well. Yes? Sorry? 30 minutes left. Okay. All right, good. Next thing I'm going to now, so we are done with interference. I've given you 2 examples. There's a lot more to be done. But let me now go to my favorite topic, which is solitons. Okay, I love these things. So let me start with a bit of history. Okay. So first, let me just tell you what a soliton is. So a soliton is a nonlinear excitation in a field, okay, where it maintains its shape because there is some balancing between its desire to disperse, like waves want to disperse away, and there is some nonlinearity that's holding it in place. So it's a balance between something wanting to spread it out and something holding it in. It's very weird because you think that waves just want to move out, but because there's nonlinearity in the system, it can hold it together. Arguably, the discovery of the soliton, as I'm showing you here, okay, was done by John Scott Russell in 1834. It's a fun story that you can read about. He was, riding along on his horse, I'm sure with the hat as well. And as he was riding along, a boat came to a stop in a canal. And as the boat came to rest, it created a pulse in the height of the water. And this pulse, instead of just sort of dissipating away, it started moving and it kept traveling without changing its shape. And he writes that he followed it on horseback for about 2 miles, and it did not change shape, it just remained as it was, and then he lost it in the woods as this wound around, as the canal wound around. So this was a discovery of a soliton. The field here is height above the surface of water. Okay, so that's the field here. So that was a discovery of the soliton. Here, by the way, you are seeing, this is a canal in Edinburgh, the same canal that John Scott Russell observed this. Of course, it's a lot newer. This is a recreation of that pulse, okay, the soliton in that more recently. Solitons are fascinating things. They appear in all sorts of areas of physics, of course, mathematics, even in all sorts of systems. For our purposes, in physics, they have been experimentally observed in optics, in hydrodynamics, in Bose-Einstein condensates. In cosmology and high energy physics, we have suggested them and we have worked on them for decades and decades and decades. Nothing yet. That doesn't mean we haven't experimentally verified them. So the green means experimentally verified, right? But there are lots of ideas for why these things should be there in high energy physics and cosmology, but we haven't detected them. Maybe we will, who knows? Okay, so those are solitons. So we are talking about solitons, or things that hold themselves together in fields, or real valued scalar fields for the moment. Say a soliton in a real valued scalar field will look something like this. Okay, it's a field that's just oscillating in this place, up and down, up and down, up and down. That's all it's doing. You would have, again, just your intuition would be that, oh, something is oscillating, it would just spread out like a ripple. But this one doesn't because of the nonlinearity. Now, the nonlinearity that's holding it together could either be provided by gravity. In that case, sometimes they're called oscillotons, or it could be provided by attractive self-interactions, in which case they are called oscillons. And they could be a combination of the two. So both are possible. We are mostly going to be dealing with just gravity at the moment. But remember, this is what the field looks like. So it looks like some fixed profile, and it's oscillating in time. And an important thing is that the frequency of oscillation will always be smaller than the mass. And you can think this through and realize that this has to be true for if this is a bound thing. Okay, otherwise things would have leaked out. So there's a lot of work on this. I wish I could spend an entire day talking about this, but we don't have time for this. So we're going to go back and restrict ourselves to gravity only case. And solitons, all of these are solitons, so we'll just keep on calling them solitons. So how do we find them in our system? I want to solve them. I want to find these objects. So let's start with our Schrödinger-Poisson equation. And solitons are ground states, meaning they're the lowest energy configuration for a fixed particle number or fixed mass of the configuration. So they are the lowest energy configurations. That should give you some sense that, oh, it might be there are attractors in the space. We might want to go and form these objects rather naturally, and that's what we see. But first, just solving for them, take the Schrödinger-Poisson system, look for a solution that's stationary, okay, meaning it has a time dependence, but there's trivial time dependence here. You plug it into the equations, you will now form a time-independent equation for the profile f. Okay, so it's a coupled equation for the profile. Not trivial, but not hard to solve. If it's spherically symmetric, a one-dimensional problem, you can solve it by what is called numerical shooting method, and you will be able to find the profile. And the profile looks like, essentially, it looks like a Gaussian, but the tail is not Gaussian, it's exponential. It's not exponential square. So it looks like a Gaussian. So somebody asked me a question about why do we get a core? It's related to this. Okay, it's related to this. Okay, so this is a solution. And this profile, by the way, is universal, meaning no matter what mass of the soliton I think about, the shape is the same. I solve it once, I know it for all masses. So it doesn't matter, you only have to solve this problem once. It's a universal shape. Again, let me remind you that in the Schrodinger system, we are solving for psi. But remember, psi is related to the real valued field with this transformation that we made. So the real value, even though psi is just going to be some stationary thing, the real valued field is oscillating because of this e to the imt. And notice that this is an I mu. There was a minus im, so the frequency is m minus mu. This is where it gets smaller than the mass. Sometimes mu can be thought of as, sometimes people call it the chemical potential. I don't like that because it confuses people. You can think of it partly as like a binding energy per particle of the system. Typically, it's the level of the kinetic energy of the particle, of a single particle inside this object, or in the environment that it's born in. So that's the solution. That's the soliton solution. I also want to show you how to get this by using our fluid equations. We made all this effort to get to the fluid equations. We should use them often. So again, if you go to the fluid equations, the equations look like this. Remember what I did. The phase in the previous case, notice this phase was a constant. Right? It was very dependent on space. So it's coherent throughout the object. What that means is that I have to set the velocity equal to, which is a gradient of the phase, equal to 0. If I do that, it just means that I have to equate phi and q. Remember this q that we had introduced? It's the same system. So equate them, and now you can get a ODE in just terms of the density. And you can solve this again. So there are different ways of getting to this. There are many, many different ways. In fact, I've just given you 2. What about, this was the profile, what about the mass of this object, of this soliton, and what about the radius of this soliton? Again, because it's a universal profile, I can actually write it down. The mass will be given, the main thing to look at first is that it's m Planck squared over m. Where did m Planck come in? Anybody? How did that come in here? The equations had no m Plancks. What happened? I've just replaced it. It's just 1 over 8 pi g is m Planck squared. Right? That's what it is. So it's just nicer to write this in terms of m Planck because this is mass. So m Planck squared over m. M Planck is a big number. Little m is a small number. So this ratio is very large. What that's telling you is that there are lots. So I can also divide by little m squared and multiply by m. It's telling you that a soliton has a lot of individual particles in it. So it's a classical collection of particles usually. Similarly, there's another important feature. This is mu over m. Remember, mu is a typical, these are non-relativistic systems. Typical binding energy is usually much smaller than the rest mass. So this ratio is small, but the combination still always remains big for most purposes. Similarly, the radius of the soliton is the inverse of this, so it's much larger than the Compton scale. So this again makes it classical. If you forget all of this, just remember that for these solitons, the mass and radius are inversely related. So m times r is a constant. If you know one, you know the other. I've told you solitons exist, or at least I've given you mathematically that that in our Schrodinger-Poisson system they exist. The more important next question you should ask, do they form naturally? Do they form from generic initial conditions? Are they relevant? Mathematically, something could exists in our system, but if it's not forming easily, we don't care, at least for this dark matter purposes. So here, this is a picture I showed you at the beginning. This is from cosmological initial conditions in the early universe. They started this as a large simulation. It is a zoom in. And this object that they see forming in the center of these halos, if you look at the density profile, which we can derive, it fits beautifully. Okay? So it is a soliton that is forming at the center. And they see it in all the halos that they see a soliton core at the center. So what does the profile of the halo look like? It's a soliton core. Eventually, it latches on with that density profile initially, and then it matches on to the NFW profile far away. So you get a chord profile in this system. What is the size of the core? It's roughly the de Broglie scale. Okay? That's the scale of what the core will be. So it depends on what the mass of the dark matter particle you're imagining you have. Is that okay? Okay, so that's one example of forming them from initial conditions. I'll give you another example, this time not from cosmological scales, but now let's say you are inside a virialized halo. And you start with almost featureless initial conditions. These are Maxwell-Boltzmann distribution of waves. I can tell you what I mean by that if you want. And this is, the color is again the density. And I'm going to start the movie. So Mehrdad, you were asking the density fluctuations, time scale. This is the fluctuation, as you say, this is not static. So this is the time scale on which this is happening. Good. Notice that you formed an object by itself. Right? Let me run it again. I don't know why it's a little bit choppy, probably because of Zoom. Should be a smooth movie. But you notice out of featureless initial conditions, this thing just pops out. Again, if you look at the profile, I'll show it to you tomorrow, it fits beautifully with the soliton, so you know it's that object. So this object emerges. This was a very nice calculation of, this was done by Levkov et al. In 2018. It's nucleation in a kinetic, what is called a kinetic regime. I won't go through the details, but you can try to estimate how long does this take. To estimate this, you do the usual thing. You want to estimate a rate, it's n sigma v. So the time scale will be inverse of n sigma v. Okay? N is the number density, sigma is the cross section, v is the velocity. But I have an extra factor capital N. Why is it there? Because we are dealing with waves. So from a classical physicist perspective, this is sort of an interference enhancement factor. If you're thinking quantum mechanically, you will call it a Bose enhancement factor. So there's an extra factor here that really enhances this rate. That extra factor is just the occupation number that we dealt with in the first lecture, the number density times the amount, this is the number of particles in a de Broglie volume. How do you estimate the gravitational cross-section? You just ask, what is the radius by which, if one particle goes by the other, it gets deflected significantly? And that's what this cross-section is. So you can put this all in, and you can estimate what the time scale is, and this is what it turns out to be. And this matches very well with the simulation. This is rough, but you can see the dependence on mass, velocities, and the density. So the denser the environment, the faster these things will form. And the lower the velocity dispersion means things are not too heated up, again, they can form much faster. Excellent question. Probably the box size. Okay. So once it forms, it kind of starts taking up things too much. But it's true, and it's a great question, and I wish I had a very clean answer. It could be related to something about periodic boundary conditions as well, because these boxes are periodic. And probably also the volume is not big enough for these. If I had a big volume, I suspect I will see more. The difficulty is as soon as I go to a big volume, there's a usual Jeans instability. So first you get a collapse of the halo. Then you get a soliton nucleating. So again, I get one object forming inside a halo. So it's a little bit, I have to do really big so I can collapse individual halos inside which I will nucleate solitons. So it's hard to do it, at least it seems like that here.
Mass is relatively large, you would have multiple inside the halo.
You could, but I think you will first, usually you will first form a halo, right? And then, because the densest region will be the center, you will nucleate something there first. And then it starts accumulating things around there. It's possible that you could have other things, but you need, along with enough mass, you need enough volume. So they're far separated, you just don't nucleate one. But I don't have a clean, to be honest, like it's a great question. I don't have an answer as to why nobody has seen multiple nucleations. It's a single one that nucleates in the box or inside a halo, but it should happen. There's no physics that prevents it completely. Sorry? Hey, I've clearly planted you as an audience. Yes, I will show you in a moment. I will in 2 slides. Okay? So. Excellent, very good eye. There's definitely a random walk because the soliton is sitting in a bath of these de Broglie waves. They kick it, right? So it does a random walk, and even at the center of halos and galaxies, you should see this jittering about. And this jitter, of course, the timescales are long, but this jitter further heats up. Remember I told you about heating up the orbits of stars? This, if you include the soliton in the middle, it heats up even further the orbit. So you would even get a tighter constraint if you had included the soliton. So the limit they had was conservative. So if you include the soliton, it should be an even tighter limit. You are, yes. Sorry, yes. Maybe the next one from now on. It's just too long. Okay, good. So this should hopefully tell you that these objects form quite naturally. I've given you 2 examples. And Rogerio asked about hydro simulations. I was lucky to be involved in this one as well, but I should say I did no work. It was Philip Motz who did it, and Anastasia Fialkow and company who did all the work. But this is a hydro simulation, CDM, warm dark matter, wave dark matter, okay? Fuzzy dark matter. This was more directed towards what is happening in the filaments and where first stars and stuff form. So that's what we were interested in for this one. And you can see the differences between what happens with CDM, the usual CDM, with warm dark matter, and with this. Between warm dark matter and this fuzzy dark matter, there's not much difference you can see. And it's true. It doesn't look very different. If you could see the density of this is for baryons, of course. If you could just see the dark matter, of course, there are differences because there are interference patterns here where there is nothing in warm dark matter.
They don't nucleate black holes.
Sorry?
They don't nucleate black holes.
They don't nucleate. I think it's hard, as I'll show maybe, it's hard for these things, even though there is a tendency for them to get more dense. So what happens, the mass goes inversely with radius. So if you collect more mass, which you should because you're just gravitationally going to collect, it should get denser. So it does tend to get denser and denser, but it's not very easy to form a black hole. It's not very easy. It's not, yes. Yes.
Then you have the sort of the density profiles of the solution, the solutons.
Yes.
And I was thinking about solutions, solutons in general. I think it is something like the
I see. Right. There are lots of there are solitons in all fields. Anything nonlinear, and people will look for a soliton there. So it's question.
Have you seen a these density profiles of these flows?
I think they're very different objects. At least I don't know exactly which one referring to, but different types of solitons will have different profiles. So it depends on which soliton you're talking about, so you're thinking in what kind of field is this soliton? Is it a abelian field, non-abelian field, or is it, what kind of field are you imagining the soliton is in?
For example, a charged scalar field.
Yes. So if it's a charged scalar field that's light, then this profile will exactly be the same as I've given you. If it's a charged scalar field with lots of self-interactions, then the profile will be different. Okay. But if it's just gravity, the profile will be the same for the charged scalar field case. Yes?
I see that in the dark matter simulation, you have a lot of more structure than in the soliton. You were only interested in the most important structure, but what about the other ones? Are you worried about that?
So this is because, remember, the reason you see more structure here is, remember the genes cutoff that we discussed? that was already saying that there's not much power on small scales, right? So that's why you don't see power here, and you see power in CDM, because CDM did not have the cutoff. So that's why you see the difference. Similarly, in warm dark matter, pre-streaming cuts off the power on small scales, so that's why this is smooth here. Okay. Yeah, sorry, I did not repeat both questions. I will try to get better, although I have no time now. I'm almost done. Yeah. How much? 10 minutes. Okay. Including questions. Okay, good. Yes. Okay. The next few slides have less to do with dark matter, but I think I'll just going to flash them through because I've talked a lot about solitons. I want to just give you slightly a little bit more, and I enjoy them, so why not? There's a little bit of miscellaneous things about dark matter, and it connects to some of the questions that have been asked of me in terms of what happens if you include the self-interaction term that I removed initially, right? There was this lambda term that I just threw away. I said it's small. What happens if you include that? What if that's very important in the system? What kind of things happen? And they're quite important for solitons in particular. So let me just show you some of the things that happen. Here, I'm now going to switch to a case first, which you are seeing here. This is a case where gravity is there and self-interactions are there, but self-interactions are more important than gravity. Okay, so attractive self-interaction are stronger. So that's what you will see here. Here I go even more extreme, and I remove gravity altogether. I'm just talking about attractive self-interaction. So we did gravity before. I'm just doing instead what happens otherwise. In reality, my research has gone in the opposite direction, as you can probably see from the list, but I will go in the way we have been doing. So I'm starting with the almost homogeneous state here. Okay, it's plain. The orange is density here. And look at what happens as I let the simulation run. Right? So almost homogeneous state. There were tiny fluctuations that your eyes couldn't see, but these solitons truly are attractors. With self-interactions, they very quickly form, and they collapse into these objects. But this is very strong self-interactions. I wouldn't, and this is a simulation done for the early universe. These are all, by the way, 3D simulations, even though I project them sometimes and sometimes I don't. Here is a case where I'm showing you the same sort of phenomena with no gravity involved. This is just self-interaction causing these objects to form. This is, in this case, they're oscillons. And this was done more in the context of reheating after inflation. This is in the inflaton field. Here is a simpler version of those to just show you in a 1D example how this thing comes about. It oscillates, there's an instability, right? The instability is because of the self-interactions, and very quickly it collapses into these objects. So it's quite generic, this kind of thing that's happening, and we can talk more about this. By the way, this was the first ever simulation that I did in my life, and it was because I was at dinner with a quite prominent physicist, and he first told me about, oh, there's these objects like this. You know, I was a starting postdoc. I didn't believe. I'm like, these things can't exist. It's a field. I know what a scalar field does. Right? It's just spread out. And then eventually, after I had to make the effort, so I decided to write up a simulation to see if this actually happens from generic conditions. And the first time you run it, this is the kind of thing that happens. It's really, the simulation was not great. Like it was not even very energy conserving, but these are really, they really want to form. And I'll show you many different examples of these. Okay, but this is, again, because the self-interactions are strong, they need not necessarily be the dark matter that we are imagining. Also, the stability of how long these objects live can be a lot less if self-interactions are important. Because now things can annihilate by the self-interaction, go into radiation of these own quanta, so that's why I don't say, I put them separately. What was the instability that you saw? You notice here? There's an instability, right? Something oscillates an instability. That instability is called the Floquet instability. I was reminded of this because of the conversation yesterday again, but let me just show you what the Floquet instability looks like in real life. This is my friend Paula Robusco. She will demonstrate to us what Floquet instability is. I hope. So she will stand. Nobody's pushing the swing, as she stands up and down on the swing, you notice that the arc of the swing increases, and it increases quite rapidly. Okay? And you've probably all, or at least some of us, some of you might have done this already, and I stopped it before she went around. So it turns out that the equations for fluctuations have a time-dependent frequency coming from the oscillations, and that's what causes this instability. Okay, so it's a parametric resonance type instability. And it doesn't happen if the potential is purely quadratic. You need some shape to the potential for this to happen. Okay. Let me end today by also showing you a picture. I told you that there are pictures, solitons. We are looking for them in cosmology, but it's nice that we actually have evidence for these objects which satisfy very similar equation, the Schrodinger equation that we have been dealing with. This is real data from Bose-Einstein condensates, and these blobs that you're seeing are solitons forming in Bose-Einstein condensates. The equations are very similar, but instead of gravity, here there's a self-interaction that's holding them together, because gravity can't be important for laboratory systems. Some other caveat, this is almost one-dimensional systems, because the stability matters based on that. So if you're interested, I can say more. I had one more slide, but I will. So the other thing I've been ignoring, I've told you that self-interaction do these things. The other thing I told you is you could have interactions with the standard model. So what would that do? Usually this interaction is weak. Okay? It's suppressed quite a bit. But in these solitons, the field amplitude is quite high, and it is coherently oscillating. So both of these things can really take a small coupling and give you a big effect. So that's what you are seeing in this simulation. I'm colliding two of these solitons, which are not emitting very easily, but once they combine, they pass a threshold, and this resonance instability kicks in, and this is photons coming out of them. Right? So when these things collide with each other, you could get a flash out of this. Again, this is parameter dependent, so it's not that every set of parameters and every system will do that, but this is a possibility that can happen. You can also think about them, what happens because axions couple to, like in this coupling, you can think of what happens in strong electromagnetic fields. All of these things become important. Sorry?
Can they meet gravitational?
I don't have a slide for it, but yes, I mean, they're blobs, right? So if they're moving around each other and they're compact enough, they emit gravitational waves, right? So they are used as mimickers as well. And we have done, I mean, not just us, but and collaborators, but many people have done simulations of orbits of these things, and they look similar, like any point masses would far away, but when they merge, the signals look different than black hole mergers, because you will not have the same type of merger event that you would expect there. One way of thinking about them is these objects are not as stiff as black holes, so the equation of state effective is different, or how deformable they are is different than black holes. Okay. I will leave this for tomorrow. So tomorrow we will start the lecture by discussing, I've told you about the scalar field, and I said, it does all these wonderful things, but I didn't give you a way. Where did we get it from? What is the formation mechanism of this field in the early universe? That I will start with that tomorrow. I will not go into very detail, just give you some couple of examples, and then we will move on to higher spin dark matter. Okay? So thank you. Yes.
So the number density of solitons is expected to be very high.
It depends on the mechanism. So, thank you. Yes. So the question was, is the number density of solitons expected to be high? So in this example, it's good because you'll see, you notice that, there's a characteristic wavelength that is unstable. So a number density of solitons is just inverse of that wavelength cubed. They basically form at peaks of this instability. That's in this case, which is the non-gravitational formation scenario. In the case of gravitational systems, it's hard for me. I don't have a good answer, okay, of this is the question Mehrdad asked as well. How many do you form? How do you form? I don't have a detailed answer for that. They do seem to form inside halos, at the centers of halos, but do lots of them form inside a halo? How efficient they are at late times, I don't know. Very long time back, well, not that. In 1992, Kolb and Takachev did simulations of axion fields in the early universe, and in the very early universe, and they also saw a lot of these objects form. At that time, they called them excitons. Those were not stable, but they seemed to form gravitationally somewhat solitron-looking things at later times. So that density should be higher, and that they have estimated, but I don't remember the number very well. But they're not quite exactly the solitrons I'm talking about. They're less stable. Yeah, I can tell you what I know a little bit more about how to estimate this roughly, but I don't have a detailed answer.
In the last slide about the opening with a photon that field solitons, does soliton continue being a solution for the Schrödinger equation?
Good. So the question was that if you couple this to electromagnetism, does the solid profile that I derived, is it still a solution? In detail, of course, no, because you have an extra term, so it cannot be a solution. But usually you can you are trying to convert the rest mass of this object into electromagnetic radiation. You have a lot of available energy to do it. At least when the process starts, it's a perfectly good solution. As if you emit, once you emit an order unity fraction of your electromagnetic radiation, or of your energy density, of course the solution has changed. It still it tries to settle into another solution. The reason it does this is when you emit electromagnetic radiation, it changes, the mass of the object changes because it's losing energy that way. But at some point the mass becomes too low or the field amplitude becomes too small that it can no longer emit efficiently. So it stops emitting again. So there is sort of a phase where it starts being a soliton, it emits, it changes, but then at some point, if it's emitted enough, it kind of just stops emitting. So then it again settles down to a soliton. In detail, in these merger things that I showed you, it's complicated. So we don't do Schrödinger-Poisson there, we do a full relativistic thing because the oscillation of the field is relevant here for this. So we actually do the relativistic simulations. We don't do Schrödinger-Poisson for that. If you just want to look at what mergers do, you can do it, but if you want the electromagnetic thing coming out, you actually do the relativistic simulation anyway.